Welcome to this lecture series in real analysis. In this lecture, we'll look at the exponential function as a certain limit, and all we need to know is basically the definition of the exponential function. So the exponential function is a differentiable function from reals to reals, which is its own derivative. So what I'm trying to say is that f prime is equal to f, and with the condition that f of 0 is 1. So that was the definition. And then we showed that it can be explicitly described, that it exists. First of all, such a function exists, and it can be explicitly described via this power series. All right. So here is the point. Here is the equation that we want to discuss. And one more thing I want to say is that we will actually be indulging in an informal discussion as to why this equation is true. We are saying that the exponential of x is this limit, and why this is true, we'll just see an intuitive reason today. A proper formal reason will be supplied when we will discuss logarithms. It will be probably in the next 2 to 3 lectures. Okay, so today we'll be content with an informal reasoning. We just want to intuitively understand why this is true. So here I have drawn the curve, the graph of the exponential function. And here is the point x. We are just trying to say that this height, this length is equal to that limit. So our strategy will be to partition very finely the interval from 0 to x. Okay, so we will do a fine partition of it. And and then we'll do something. So here is the diagram corresponding to the partitioning. So we have partitioned the interval 0 to x into n equal parts. Each part has length equal to x by n. This is x by n, the next is x by n, this is x by n, and so on. And therefore, the first real number that we see here is x by n, the second is twice of that, the third is thrice of that, and so on, up until the last one. The last one is x, but we have written it as nx upon x. Okay, great. The value that the exponential function takes at x by n, we have written as h1, h2, h3, and just so that we have a convenient notation at hand, let me express x by n as x1, 2x by n as x2, and so on. Okay? So hn is nothing but x of x. And since this is not so easy to write every time, let me denote the exponential function as f, just for convenience of notation. Okay, so the main philosophy or the main equation that will guide us to an explanation is the following, which you must have seen in high school physics. So this is approximately equal, not equal, but approximately equal. Right? This is nothing but the first order Taylor approximation. That's all this is. It's just that when you do Taylor approximation, you can't write an x here. You have to write something else. You have to write something between x and x plus delta x. Then it becomes an equation if you suitably place the real number here. But informally, you can write this. It is a good enough equation for us to explain a lot of things intuitively. Okay, so let's get started. So first thing we'll do is we will approximately write what is h1. So h1 is nothing but the exponential of x1, which we are writing as f of x1. And we will write this as f of 0 plus x1. And in fact, x1 is nothing but x by n. And think of this as a small number, which is what is typically denoted by delta x. Delta x is not delta times x. Delta x just denotes a small number. Small in an informal sense. So f of x1 is equal to that. And now if we apply this equation, then we get this is roughly equal to f of 0 plus delta x times f prime 0. Right? Immediately by that. But since f is the exponential function, f prime 0 is just f of 0, right? And now we can pull out f of 0. So we get f of 0 times 1 plus x by n. correct? But f of 0 is 1. So this is equal to 1 plus x by n, and we end up with an approximate equality, which is that h1 is approximately equal to this number. Okay, we can play the same game for h2, which is f of x2, which we will write as f of x1 plus x by n, right, which is equal to, or approximately equal to, f of x1 plus x by n times this number, right? Again, we have just used this equation, but f prime x1 is f of x1 because f is the exponential function, and we can now again pull out f of x1 to get this. But what is f of x1? I mean, what have we approximately written f of x1 as? This number. F of x1 is nothing but h1, which is approximately this number. So we can write this is approximately 1 plus x by n whole squared. And if you just keep continuing this way, you will say that h of n, which is f of x, which is f of x, which is exponential of x, is approximately equal to 1 plus x by n to the power n. And it is conceivable that as you take n to be very large, this approximation will be better and better, and hence in the limit, the limit will exist and will be equal to the value of the exponential function at x. Again, this is just an informal explanation. This is not a proof. Later, when we discuss logarithms, we will give a proper proof. And I would just like to end it here. As usual, like, comment, share, subscribe, and I will see you next time.